This is might be some that might seem embarrassing. This is just new topic, new talk, new concept. So sometimes when you're just about to start, you have to regroup your thoughts, and that's what just happened. Hello, my name is Jakub. I came here from Gdańsk. It's not the first time on GeeCON, which I'm very happy about. And today I will talk and I will try to drill down some of the serverless runtimes. And the concept of serverless, and not about evangelizing about AWS Lambda or Google Functions, but more to understand what should we expect from serverless. What just happened? Yeah, what should we expect from a serverless environment, whether it's a function or a database, and how it works, what are the gotchas, and how we can work with it as an engineer. So obviously there will be some cats because I'm a cat person, and there is a Slido where you can ask questions, but I think you know the drill. So let's start with the serverless itself. It all started with AWS Lambda, but we'll take it more generally as serverless. 2014, if I remember correctly, so it's already 10 years. Lambda or serverless lets you run code without provisioning or managing servers. That's the promise. You pay only for compute time you consume. There's no charge when your code is not running. That's exactly what AWS is saying about its Lambda. And with serverless, your code runs virtually any type of application or backend service or whatever with zero administration. So no more servers, no more upgrades. It just happens. It's like magic. That's what cloud providers are promising. So we can say that in old money and the old times, when we're about to deploy anything anywhere, we have to figure out how to prepare our instances, how to prepare our servers, set up something, set up our runtime, prepare the application, deploy, then monitor the app. That's really helpful. And then pay for the time it was running. Do all the security patches and all the upgrades. But as engineers, we are really interested in this green part. We want to build an app, deploy it, operate it, and pay. That's less funny part. So what it led to is we're paying for cost of the hardware, whether our application was running or not. And it was usually derived from the number of CPUs and memory you were using times the hours it was running. So if we take an average instance and AWS, 8 CPUs, 32 gigabytes of RAM, that's about $500 a month. Whether there is traffic, whether there is not, that's what we pay. And then serverless promised this new economy where we don't care about instances, the preparation, the setup. We build up, deploy, monitor it, and pay only if it's used. So it comes with a promise that what you'll pay for is just the actual usage of the application. So there's something you pay for the requests and something you pay for the time application spends spinning CPU, using memory, whatever. And that gets tricky because you kind of, when you run a function, when you run your simple code, you can reason how long it's going to take, but the more complex it gets, it's harder to understand. So if we take the graph that's from a few months of our AWS account, you can see that it changes. The green one is the EC2. Removing EC2 instances is always cheaper. But there's a trick. The orange one is the Lambda, is the AWS. And you can quickly get into a situation where it's totally out of control in its cost because you pay for how long it runs, and it's much harder to control. So it gives you this promise of infinite scaling or paying exactly what you want, but then it can get out of the control. And that's something I would like to talk more about and give you some understanding how it works internally so we can fight that unpleasant surprises. So how it works. When you go to AWS Lambda, to tutorial, this is pretty much what AWS tells you. Just write this handle function request or handle class deploy, and we are ready to go. But yeah, how it works. So if we try to decompose it, we have this invoke. We have this invoke function thing where we have an HTTP trigger or some scheduler that runs our function that triggers it. Then there is some magic, there's some sharks. Then our code gets called. Then something else happens which we hardly know about. And then we have a blip on our dashboard that the execution was successful. So let's dissect it. Let's dive a little bit deeper of what's happening underneath. So we can conceptualize about having two environments or two parts of the execution environment. We have something where we deploy or configure our functions and something that actually runs them. So we have a part where we go to AWS endpoints or any other cloud provider endpoints and say, hey, this is our code. For simplicity, I'll just say we are running Docker, but you can do different things. So we have this thing where we tell, okay, this is our function, this is how we would like to run it. We roughly need 1 GB memory, half a gigabyte memory, depending on what we're running. And this is the binary part. This is the image that we would like you to run, and that's pretty much it. And then in the execution part, it gets more tricky. So we have this trigger part that the cloud provider handles. This can be an abstraction over a load balancer that responds to HTTP request. That can be a scheduler. That can be messaging system. It can be a consumer of AWS or any other cloud provider events. Many things. And when a request comes in whatever form, we have to check if the function exists. Okay, function exists. We know how to respond to that request. And what is happening later? We take this Docker runtime. We can take this Docker image and deploy it. Do the Docker run, and it runs. But how the container we are running is able to understand that it's supposed to respond to any Lambda call. So, well, we can think that once it's started, it can query something, whether it's a trigger or any other environment. We can say it's a trigger here, and pull the next request that is waiting for him and gets a request body in return. And when it's done, it calls another HTTP endpoint saying, hey, this is a response, and we can forward this response to HTTP response if that's needed, or just disregard it if that's just a scheduled message. So we can say, well, that looks very, very simplified, and does it really work like this? Funny enough, yes, in AWS Lambda, that's exactly how it's working. So let's step further, one step deeper. Let's run some code. When you go to AWS Lambda, there is a set of runtimes, and I am taking AWS Lambda not because that's the best. It just happens that I've been using this most frequently, and it's easy to. It's a good example. So we have all those runtimes for different programming languages, and that's what you've seen with the Java example. But there are two fun parts, which is called OS-only runtime. And I don't know if you've come across that with your cloud functions, but this is pretty much serverless bash. So when the Lambda is triggered, Bash is initiated, and that's all. But if we look deeper into that, that's a Docker definition for our Bash Lambda. So we have a few interesting things. We want to use a cloud provider defined base image, which is in this case Lambda. And we have something called Bootstrap. That's what AWS is telling us to do. And we have our script that is actually doing the application logic. Our script is very simple. It's just a handler function. And you might wonder, why in the world is somebody writing a serverless function in Bash? Well, one answer is that because it's possible. And the other is, sometimes Bash is a good runtime environment if you just have to trigger some SQL scripts, and the best tool for triggering SQL scripts is, for example, PSQL. So you can wrap your execution in Lambda and just run it. Works. But then if you go to our Bootstrap code, a lot of Bash, but I will run that through you. We have this HTTP next endpoint, which pulls the next item, work item from our environment, and we have this submit completed result endpoint, where we send whatever we've done. And the one in the middle is just invoking the handler. So this very simplistic example actually works, and that's just running in the while loop, and that's how AWS is figuring out whether there's more work for our Lambda. That's the simple part. So we have this simple example, now we run it, and the question is how much we're going to pay for it, and how we can figure out how much it costs. So from the earlier slide that I had, we had a concept of paying per request and paying for the execution time. So if we get to our image, where we kind of designed or conceptualized the Lambda environment, we have the green part, which is the request, and that's one part we are paying for. And that's the second part where we pay for the time spent between, let's say, the Docker run. I'll get into that later because that's not very exact. And before submitting the response to the environment. And we pay for this processing time. So very good question that immediately arises is, okay, that's very cheap in the beginning. When is the moment that I'll start paying more than for allocated prepaid hardware, which I usually did on my cloud environment, where I said, I'll have this hardware 24/7 for a month, whereas Lambda is just now and then. So obviously you can plot a graph. And it appears that roughly, if your Lambda is running 24/7 and is comparable to a small instance of a EC2, it very quickly, after like 40 hours, it gets very expensive, much more expensive than a pre-allocated hardware. Why is that? If you look how much to pay for the Lambda or for any other functions, you pay for the number of requests, that's one thing, and you pay for how long the duration of the function. You pay for the duration of the function, how long your code is running. And this is called, in many systems, gigabyte seconds. And we get into the very artificial unit that we are charged for any serverless runtime. And this is, I think, the most tricky part, which I'll focus a little bit now and further into the talk. Because that's the number of seconds your code was running, depending on the amount of memory that it has been using. So for just a function, for just a simple code that is running, yeah, you can kind of calculate it, you can kind of assume it. though it's much trickier than calculating hours of your hardware. The other question is this all? Because my code is running for a fraction of a second, but there is some time that is spent like spinning up the Docker container. If it's just a bash function, it's milliseconds. But you know, the container has to start, yeah, it's another hundreds of milliseconds and so on, and then so forth. So in the traditional, we had this traditional time model, and as it gets replaced by unit, on one hand, we are told we will pay only for what we use, but it's almost true. Because if we recall this picture, we had this Docker run thing, which is not actually serving the request. And we have this big while loop that was spinning all the time in our Bootstrap code, which is also kind of not serving the request. Do we pay for it? So when you look deeper into Lambda or any other serverless runtime, you have this concept of cold and warm services, or cold start duration and invocation duration. So when you do your Lambda, or when you do your serverless functions, you have this part where the service downloads the code or downloads the Docker container. It's usually the hub is pretty close to your environment, blah, 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 but there is a time spent doing that. And then the execution of the program starts. That's another part that is happening, and that's not totally related to handling your request. And then you initialize your code. So if we talk Java, this is starting the Java virtual machine, and this is doing all the dependency injection before, or initialization within my lab before I can serve my first request. And then the execution handler for my code is being called. So we have downloading the image, something like the Docker run. We have the Bootstrap that you've seen, and this is actually my script that is being run. So as you can imagine, and that's pretty much what you've heard all the times when anybody told you about the serverless. Yes, if you use Java, it has the long start, you have this cold start thing, you will pay for it, blah, blah, blah. Yes, and that's where it's coming from. And whereas if it's just a function handling individual requests, that doesn't seem very much important. But now imagine where we're coming next. You're having a database. You're having your data that got called, and now you're starting it up. So is this time comparable? Do you have also the cold start concept? We will get to that in a second. But before we get the cold start, so we have this concept for, and that becomes very important for the serverless, that the application hasn't been used for a while, and now it takes longer, a little bit longer to start and to handle the first request. There are two immediate questions that one might ask. How long it takes for the function to start running? So it depends obviously on your function. What's a couple of milliseconds or a few hundreds of milliseconds, depend how complex it is, what programming language you are using, and so on. The other question is how long it's going to stay warm. So how long this while loop you've seen in the bash script will keep on running, so that when the next request arrives, it will be served immediately. Obviously, nobody knows that for sure, and that's one of the things that cloud providers never tell. You can try experimentally, and depending on the size of your function, whether it's 1 gig, 4 gig, half a gig, in terms of memory, it can be 5, 10 minutes. Usually, the smaller the lambda, the smaller the function, the longer it can stay warm, which is quite a good incentive to build very small environments. Okay, so we go through the very simple Lambda example, or simplish Lambda example, to understand what's cold and what's warm, and how the code is being evaluated and invoked so that we can serve the request. Now it gets to something more profound, more complex, beyond a single function. We've seen that the function was sometimes hard to control in terms of money spent, in terms of how much it's going to cost. So how it works with the more complex things. And when we go to, or when we Google or where we search for different platforms, databases, and the term serverless, it appears that it's quite popular. So AWS announced like Elastic Cache serverless. So you had Redis, now you have Redis without a server. Red Panda is doing Kafka replacement and a serverless. So you can think, serverless Kafka, how cool is that? I was working personally in Hazelcast for a while, and Hazelcast has this Hazelcast platform, serverless. And CockroachDB is a table, I think, database, and also serverless. And you can go on and on, Postgres, serverless, and so on and so forth. So you got quite a few products with this promise of being serverless. And if there are no servers, and we are running a database, or something persistent, like Kafka, there are a few questions we start asking ourselves. So how we are going to pay for that? That's one thing. When we run Redis in the past, or Postgres in the past, we allocated an instance of a certain size, and we were paying for it no matter what. And now what? We will just pay when somebody calls the service, or are there any more costs? Am I charged all the time, or again, it's a serverless, am I charged only when it's used, when somebody uses that? And if nobody uses that, what happens with my data? So if it's a serverless Postgres, is my data kept? Well, I hope so. If it's a serverless Redis, which is in-memory storage, in-memory cache, what happens with that data if it gets called and disappears? And is this data always available? Can I call it any time? Will it just come back? So we had this gigabyte seconds, talking about the payment, which we've seen for Lambda. And we have a similar concept for persistent storage, but it's just getting more and more complex. So when we have Elastic Cache, we obviously know we will pay for the data stored. And there's this part, you pay for the data stored in Elastic Cache serverless, blah, 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 built in gigabyte hours. So every hour we store 1 gigabyte, we pay for it every hour. That's obvious. But then we have this other part where you have this weird Elastic Cache processing units that serves that states that every read and write of 1 kilobyte would consume 1 unit, and then you will pay for it. So it's getting really hard to estimate the cost, how much I'm going to pay for it, and whether I'll exceed this threshold, which we've seen on serverless, on the functions, or not. If we go to, and well, Redis is simple, or Elastic Cache is simple, it's a key value store. So there is not much I can do with my data. I put my data, I've put 1 gigabyte, and I will retrieve it, so I'll pay 1 gigabyte for storage, and 1 gigabyte derived in this eCPU units. That's okay, that's understandable. But then if you go to something like CockroachDB, which supports SQL, PostgreSQL and supports all those Postgres operations and aggregations, which become more CPU intensive with every operation and with all the operations you're trying to do. You obviously pay for storage. But then you pay for your queries, for your bulk operations, and for some background jobs, because that's what you can do, and then for some statistics. So you start to pay not only for the SQL query you're running, but you will also pay for your explain query to your SQL query if you run it. And if you connect your CockroachDB to any external data feed, yes, it will again start to incurring some cost, and Cockroach calls it request units. Another abstract term, another term that you're not able to easily conceptualize. So it's getting much harder to understand if the price I'm going to pay for my serverless database is going to be remotely equal to what I'm going to pay if it's just running a normal standard hardware. Yeah, but now you at least know. If you go to Kafka or Red Panda in that case, it gets even more complex, because you not only pay for data, you not only pay for data that you write, you pay for the data that you read, you pay for your retention, so how long the data is stored, and then you pay for your partitions and so on and so forth. So it's getting even harder to understand it. And the reason is, so if you have a key value store, you might have a very simple query. You do select, couple of fields, join, and that's it. You put data in, you put data out. But then if you have more SQL support, then you can do some aggregate functions, counts, mins, minimums, maximums, and then look up data from another table. And this is really hard to estimate in the CockroachDB request units. So that's much harder to upfront estimate how much I'm going to pay. And then I'll give you yet another example, because Cockroach allows you to run some more profound SQL code, but there's the platform like Hazelcast that allows you to run Java code. So you're moving from gigabyte hours, which are a very nice term for something that is memory bound, and you're going towards something that is very CPU bound, and you're doing more and more CPU work. That is very hard to estimate. It's very hard to predict how it's gonna cost you, and it's equally hard for anybody who is building up this kind of a service to come up with a good term. So let's dissect how this serverless database might look like, how it can be built. Because one thing is how much you pay for it, and the other is how it withstands the promise of the guarantees that you will never lose your data, that the data will be available, and at the same time, it's not a service that is running 24/7. So I'll run you through an example how we built it some time ago with a Hazelcast, which is in-memory data platform, but conceptually that works the same for Redis, and it's very similar to Red Panda. The concepts holds. So we have, again, a part where we deploy things or we configure things, and the things that we are executing. So for Hazelcast, how we built it was kind of an orchestration thing and a metrics hub. These are two important bits that are being used. Obviously, there's much more, but when you deep dive into any of those architectures for any cloud providers, that's roughly follow the same lines. And there is an execution environment where the cluster will actually running, one of them, multiple of them, whether it's a Hazelcast cluster or a Redis cluster, and some additional storage, like S3. So you go to the orchestration layer where you can define and configure your cluster. You can create it and you can manage its deployment. And then you have the second part where your application connects, and that terms Hazelcast client. But if you're running Redis, that's a Redis client that uses some Redis protocol that goes to your cluster. When it tries to connect, the first thing that needs to happen is to deploy the actual cluster. If you're starting from scratch, that's easy. That's usually deployed straight after you start, but sometimes it's deployed and it's shut down because nobody's using it, and that's redeployed. We'll get how that's usually implemented. But yes, we have this deployment process. The cluster is started, and then, in most of the cases, there is this automation of pushing up metrics, and based on metrics, a lot of those services are actually figuring out if your database or if your persistent store is actually working. Let's call it orchestration layer, but a control plane service is looking on not only if you're using it, but also how much you are using it. Are you exceeding certain threshold, because auto-scaling is a part of your serverless? And whether everybody or all the clients disconnected so we can shut down. So we have this usage and scaling orchestration. And when we decide to shut it down, the data is backed up to the S3 or locally and then moved to the S3, so it's persistent, and regardless on what happened, you can always recover your data. Some of you might wonder, okay, but how it's going to work? There are three concepts we can get through in this traditional versus serverless operations. We can have the process of connecting to the cluster, so how those clients know that they have to connect somewhere and the server needs to start. Sometimes the client goes through a proxy, connects to one member, and then the traffic is being dispatched. Sometimes the client needs to connect individually to each and every node in the cluster, and so on and so forth. There are different topologies, and somehow that needs to be handled. Then there is a process of recovering the cluster from the full stop. So we've connected, but how we can intercept to get the data back. Yes, and how we can intercept whatever happens in the cloud environment so that we are able to back up the data or take the data if the cloud provider, if the cloud scheduler, whether it's a Kubernetes or ECS or whatever else, decide to kill the cluster. So let's quickly get through those three. Hazelcast, again, an example, but any other client, but I have just working code from Hazelcast. You can have a client config where you define what IP addresses, what are the IP addresses of your nodes. That's very static, but that's kind of the default. So you have the IP addresses, and you have this concept of the smart routing in the Hazelcast, that the client know exactly which node to hit with its request. But then if you deploy exactly the same cluster on AWS, your client configuration changes, because you don't set IP addresses, because IP addresses in your cloud provider are ephemeral, and you set up your access key, your secret key, your region, and the service name of your cluster, so the client can figure out how to connect. And then when you go to the serverless environment, to the cloud, to the serverless cloud, in most of the cases, those providers give you, wrong order of the slides. It gives you additional functions on your client where you, for example, say, okay, but I want to provide to the serverless environment where you define the endpoint and some token for authentication. And it serves multiple purposes. It lets you validate your credentials or authenticate. It checks underneath if the cluster is running. And this is the moment when the cluster starts if it's needed. So that way, in most of the cases, we can block your call, we can block the client's call and start the cluster underneath. The ultimate question that they raise is, hey, I'll be waiting for that. Well, yes. So it returns an up-to-date addresses of the database, but yes, there is a waiting time for my cluster to start. And this is exactly the same as we have in our functions. Cold start, this is more or less where the cold start for the servers happen. So how long will it take? And that gets to us to recovering the cluster from the full stop. How long it takes? So if you take Postgres database as a serverless offering, which is available, they say in their docs that can take from 500 milliseconds up to a few seconds, depending where your cluster, what's the connectivity, and blah, blah, blah. So there is a waiting time before your cluster gets back. If you get to the CockroachDB, again, serverless, they say, well, typically around 600 milliseconds. Yes, you can expect more. Sometimes you can expect less, depending on how much data you've stored. When we were doing Hazelcast, it took us a few seconds, also depending how much data we had to transfer from our S3 buckets, in that case, or our cheap storage back to the cluster. But that's recovery. We've been working with Kubernetes, or we've heard at least about it. We've been working in the cloud, and we know that if there's one thing we can be sure about is that our servers can be shut down, can be killed randomly by the cloud provider, because that just happened. So we also need a way for us to understand that the server or our process, part of our database, is about to be shut down, and we want to collect the data, we want to collect the backup. And actually that happens very naively as well in many cases, because Linux has this concept of signals. So there is a way for processes to communicate, and whenever, even if it's running in Docker, whenever Docker supervisor is trying to kill our app, they send a signal, SIG term in Linux terms, so kind of, hey, can you please shut down? And that's how most of those containers are working, and that's kind of a Linux standard. If you go to AWS documentation, their load balancers are working exactly the same way. If a target of your target group, so your server is going to be shut down, yes, load balancer is draining and is removing the target group, and once it's done, it sends signal to gently shut it down, and then kills your target completely. And that's exactly where you can hook up, and that's where exactly those serverless cloud providers hook up to collect your data. Sometimes as simple as that. So you can trap a very individual signal, whether it's bash, whether it's Java code, doesn't really matter. And then you can do some operations before it actually gets killed. And all of the cloud providers are very blunt about it, how much time they give you before they actually send a SIG kill signal and try to kill your application. So that's how those in-memory servers or those serverless servers manage to withstand the process of actually killing the environment. A few final words. There's some takeaways, which I would like to leave you with. So there is no free lunch, which is obvious. There is a minimal fee, which can quickly get out of control, and we have to be aware of it. As you've seen, it's fairly easy to start with a small Lambda, and as the usage grows, you can end up paying significantly more than you could have paid for servers. There is no free lunch in the sense that serverless apps require different design to avoid some unexpected cost. So one of the biggest mistakes we've personally done is we've designed a Lambda also, or guys on my team designed a Lambda, and this Lambda was orchestrating calls between a few other servers. So this Lambda was mostly waiting. It was just, HTTP call and waiting for the response. So we paid a couple of $100 for just waiting and doing nothing. Yes, that's a mistake you can make with your Lambda. And last but not least, if you got hooked up on the serverless ideas, this lower cost comes with some latency variability. So if your requirements are, or if you want your application to be ultra low latency, that's probably not for you, obviously. But if you're just experimenting, if you're doing some batch jobs, if you're doing some synchronization, if you're doing your password rotation or exchanging some tokens, that's where the Lambda works. That's where this additional storage of serverless, Postgres, or whatever can be really, really helpful. So that's for me. If you have any questions, there is this Slido thing, which I haven't set up here, but we'll try to do it now, or I can take the questions. What just happened? Yes. I'll do it on my phone. Are there any questions? There's nobody from GeeCON. I have to do it on my own. Okay. Bear with me for a second. Technology. Oh, come on. Which room we were in? Room 12? Okay. Slido.com. GeeCON. Oh, I had it. Room 12. Maybe it's the wrong. No questions so far. Okay. So thank you very much.